EP Drinking Water Program, EC, SDC Training Webinar, Key to Manganese Treatment, Technical Support, and Grant Programs, hosted by RCAP Solutions. Today is September 16th, and we're glad to have you here. This session is being recorded. We'll be putting this on YouTube later. Keep this in mind just for your FYI, and we'll be able to send everybody the link later on too. You're on the GoTo platform. So if you're not used to the GoTo platform, let's go over how to use the features. Where it says hidden at the top, there is a little drop-down caret. This controls what you view on the screen. So if you want to see everybody talking, you can. If you'd like to not see everybody talking, you're also welcome to do that as well, which I'm doing right now, actually. Another feature on here is, one second. All right, so over here in the corner is the chat box. So you can ask questions in the chat window or read them aloud during the Q&A at the end of the session. So please just hold your questions to the end. And my coworker will be funneling through them and seeing if they're repetitive or maybe they're answered throughout the actual session. So this is where you're going to chat. Also, if you have any tech issues, can't hear, can't see, you're having some problems, please go talk in the chat and my coworker will be happy to help you with any technical issues you're having. We're asking people to go off camera if they wish. It saves bandwidth. We'd love to see your beautiful faces, but if you don't want to be seen, that's okay too. You're more than welcome to turn off your camera, which is going to be at the bottom. Oh, sorry. To the right here are the materials. So the materials are going to include a PDF for this presentation. So it's a little icon with a little paper clip and it says materials. Just be aware though, you don't want to X out of you want to close out of the materials with a little X there, not the bottom of the screen. You will leave the entire session. Don't hit where it says leave. You want to close out of the materials tab. So that's one way to view GoTo. Oops. Sorry, one more thing that's important too is, yeah, again, if you want to go off camera, you're welcome to. And everyone is muted. It's not a personal thing. We don't want to hear you. We just need to keep it muted just to keep the presentation moving along. GoTo Training mobile app, same thing. Bottom of the screen, it has a screen sharing option. You can view different presentation modes. There is a chat feature as well, and the material. So it's at the bottom of, if you have a tablet or if you have an app, it's at the bottom of the screen. This session is brought to you by RCAP Solutions, a nationwide network supporting rural communities. We're in the Northwest. We are called RCAP nationally, but we are called RCAP in the Northeast. We are also the Caribbean. We are a nonprofit organization that provide technical and training help to small towns with drinking water, wastewater, treatment, utility funding, and community management. My name is Danielle. Pern and I will be your hosts and tech support. So please reach out to us in the chat box if you have any tech issues. Oops, sorry. Sometimes I have a bit of a lag on my end. Just give me a second. All right. Certificate requirements. So to get your TCH credit, which is up for grabs, you need to be signed in from your unique link joined on your own device. You need to participate at least 75% of the tests and polls. We have no tests, just polls. Be here for at least 90% of the session. If you have to leave or something happens technically, tell us in the chat. I'm having connection issues. I'm having Wi-Fi problems. Let us know you're trying to be here. We do count effort. At the end of the session, a evaluation will launch. You need to complete that. And a link will be included in a follow-up email. This is very important. I will go after people via email politely if you do not complete the evaluation. You'll receive your certificate in 2 weeks via email. So just please be patient. Sometimes we have a lot of people in these. Just hold tight. So something very important to know is, or earn credits, we like people to not share a monitor unless you have to. So here's a quick poll question. How many people are attending at your session? I'm going to launch the poll. We just want to know, because if multiple people are sharing at your monitor, please write in the chat the people that are at your monitor with you. This is not recorded on a video portion. We just want to know so we can keep track of who's attending and who I can be sending TCHs to. And if you are sharing, please put in the chat your answers. I need to know that you are trying to participate. And Perna, if you can keep track of those people and those groups, I will be probably emailing people later to follow up on that. I just want to make sure that we have a good kind of range of how many people. Okay, so 83% are pretty much on their own monitor. It happens. I know some offices have one monitor for 10 people. It does happen. All right, give it like another 5 seconds here and I'll close out this poll. I don't really need to show these results because I already know. So like most of you are on your own monitor, but we've got a few people that are groups. So again, in the chat, please tell us what's going on. That way I know. Next poll question. I want to know who's in our audience today. Are you an operator in training? Are you a board member? Are you a water system admin? Are you on the regulatory side? Are you, like me, a technical assistance provider, a consult, or not a system? We just kind of want to know who's here. And also these polls are important for us to kind of just see who's in the audience and who we can talk to today. All right, launching. I'll close on the polls and on my end, I'll see like 90% and then I'll read out. All right, we're at 76%. Give it like 10 more seconds here.
Well, Daniel, the number may not go up significantly because we have presenters from UMass and us. So
Yeah, that's what it says. Like I figured that too. Like if people are, yeah, I always consider that. I see all the logins after I know who's in
yeah,
it, so I know I usually just have like a whole like DEP count. Depends on what kind of data people want. Sometimes they want to know like how many, they want me to aggregate the data after. Okay, I like to see it at 80%, so we got 79.
yeah.
One more person vote. Come on. Again, if in the chat, just let us know. You can just put like your group and just say kind of what your group is. People they name their
Yeah.
group. They have like a team. We'll say like team water system. All right, 82%. All right, let's share these. Oops, share results. All right, so we got 43% operator in training, 4% water system board member, 0 admins, 29% regulatory, and 25% TAPS consultants are not a system. Interesting. All right, I got one more poll for you guys. So these are fun, right? What is the population of your system? If there is a do not know, don't worry about it if you don't know. Let me see here. Launch. Are you 3,300 or less? Are you between 3,301 and 10,000 or over 10,000? Not a system. You can check that too. %. Oh, I'd love to see a 90%. Come on, more person. Yeah. I was like, it makes me happy. Like one time I had 100% all the time. I'm like, yay, it's so rare though. Come on, one more person. Maybe it's 2. Almost there. Okay, close enough. I got 89%. All right. Sharing the results, we got population 3,300 or less at 26%, population 3,301 to 10,000, 3%, population over 10,000, 16%, and then unknown or not a system at 55%. All right, introducing our fabulous speakers. John Tobiasen is professional emeritus and part-time research professor in the Department of Civil and Environmental Engineering at UMass Amherst. He is a UMass co-principal investigator for the UMass DEP-sponsored UMass EC-SDC Implementation Support Program. Also joining us today is Abby Jacobs. She works in the Emerging Contaminants Small or Disadvantaged Communities. That's what that acronym is, EC-SDC, Program Grant Manager for the MassDEP Drinking Water Program. She has over 10 years experience in the drinking water field and holds an MS degree in biology and a BS in marine science. And all of John's degrees are listed on his slide here. All right, I'm going to hand it over to John now to take over the presentation. And I'm going to go off camera. All right.
Right. I'll go briefly on camera for a minute, but hopefully you're seeing a slide, and I'm going to put it up into presentation mode. Is that good? If somebody could confirm that.
Yep. Sometimes it takes a few seconds.
Is that good?
Yep.
Good. Now you're all set, John.
All set. Great.
All right.
Hey, thanks everybody. All right. Pleasure to speak with you. Our agenda is we're going to talk a bit about manganese, which is the thing I'm going to cover, a bit about the technical assistance from the UMass side of things, and Abby will take over and describe the grant program and some other features of the program. I'm going to go fast. The slides are here for your future reference. So we have a joint program that supports several of DEP initiatives. In this case, it's the ECSDC grant program. And today I'm speaking about one of the contaminants. And one of the things you might ask about manganese, and the question I have, an emerging contaminant, really? Question mark. Manganese has been around a long time. It's a huge component of the Earth's crust. It's not something that that you would think of emerging. But for the US EPA, emerging contaminants are defined based on their occurrence on what are called contaminant candidate lists, and these are things that might occur and have health issues, and they have potential health issues. And some of those contaminants that are nominated get monitored. So, for example, manganese was on the contaminant candidate list 4, not on 5, and the levels were assessed in what is called the Unregulated Contaminant Monitoring Rule, or UCMR 4, which occurred in 2018 to 2020. Another example would be PFAS, which has been on CCLs and was assessed in the UCMR 3 and is just completing being assessed again, a bunch of compounds in UCMR 5 going on now. So one reason to mention PFAS is that manganese and iron are very common treatment challenges, and they very often co-occur with a treatment challenge such as PFAS, and they can't be ignored. They can dominate and have a huge impact on whatever we do in treatment, so we have to pay attention to them. So a couple of quick overview. I'm going to mention iron a fair amount because they do co-occur, and one of the things I want to point out is that in our business, people say iron and manganese, iron and manganese. And it's not a word, it's not a thing. There is manganese and there is iron, and they're distinct and different, and you got to pay attention to their chemistry. It's a very common need. There's a lot of myths. It's oversimplified. They actually have interesting and complex chemistry, and it's easy to make mistakes. And I'm not going to talk much more about it today, but lack of characterization of the forms of iron and manganese is important. What I mean by form is whether it's particulate, colloidal, or dissolved. So the concerns arise largely due to aesthetics, due to discoloration of fixtures, cause of turbidity, scaling, staining surfaces. And we have US EPA secondary limits or aesthetic-based limits of 50 micrograms per liter or 0.05 milligrams per liter for manganese, and 300 or micrograms, 0.3 milligrams per liter for iron. However, long been recognized by many in the community that the treatment goals to avoid chronic problems with these metals. Manganese should be at 10 to 20 micrograms per liter or 0.02. Below that is a way to avoid chronic problems. And iron, I say less than 0.1. It just turns out it's really easy to achieve iron levels of less than 0.1. Manganese, not so easy. What about health concerns? Well, the reason manganese was on the CCL is that EPA has a lifetime health advisory level, has had it for a long time, of 0.3 milligrams per liter, and thus it was on the monitoring rule. The World Health Organization put out one of the lowest health-based limits, a guideline of 0.08 or 80 micrograms, and Health Canada in 2019 set a health-based standard of 120 micrograms per liter, and they set their aesthetic goal at 0.02 milligrams per liter. There are no health-based guidelines for iron, as that has not come up in that regard. But iron and manganese get precipitated as oxides, and they're often carriers of other contaminants such as arsenic or lead or chromium, things of that nature. So where do they occur? In groundwater sources, they occur in wells because of the reducing conditions in groundwaters, often related to microbes that shuttle electrons to metal oxides and reduce the metal chemically to soluble forms. Often in wells, the concentration can be very stable over time, but wells not so far apart can have very different concentrations. And there's other co-contaminants such as arsenic, hardness, radionuclides, natural organic matter, etc. In surface waters, it's usually a variable condition seasonally because some surface waters, lakes in particular, get anoxic hypolimnions, the base of the lake, in the summer, and can lead to reducing conditions, summer, late fall, and release manganese and iron from the sediments, which then can come into intakes. Usually in run-of-river sources that carry some turbidity, manganese or iron are usually in particulate form, not dissolved form. Unfortunately, there's within drinking water treatment sources of iron, of manganese in particular. So in sludge, in clarification processes that create sludge, manganese in particles can become reduced chemically or biotically. Backwash lagoons, dewatering systems, recycle streams can have that. And unfortunately, the coagulant that is sometimes used, ferric chloride, has often had a co-contaminant of manganese, such that in some cases, some very notable ones, large ones, manganese all of it came from the iron coagulant and caused a problem for this system. And also we make use of, and you'll hear me talk about, manganese oxide coated media to remove manganese. And if you don't keep oxidative conditions across that media, it can release that manganese into solution. So what are the approaches to take care of manganese and iron? And I'm going to list two here and then a third comment. Well, first, there are things you can do to minimize in the source water, and that can be selection of wells, blending of wells. In surface water, it can involve reservoir aeration and multiple intake depths. I'm not going to talk about that. We're going to talk about removal options. We're going to go over that. And then one that gets mentioned, and particularly for small systems that the industry has used over time, is an approach that is not good, really. It's called sequestration. And the idea of that is to add a chemical that prevents the oxidation of reduced iron and reduced manganese such that it doesn't stain fixtures or go on pipe walls. And we deliver it to the consumer in that sequestered form. Unfortunately, it's rarely all that effective, almost never for iron. And what happens is a lot of those metals just get deposited in the distribution system, and you see them in flushing events and bad water events, and it just creates a future problem that we often call legacy manganese out there. Or it happens when you add base, as in bleach, to laundry, and there you get to oxidize the metals onto your clothing. So the forms of dissolved in particulate iron or manganese and iron, I'll focus on manganese here. Mn2 plus or Mn2 is reduced and it's soluble. There's a minor amount of some other inorganic anions. And then the other dissolved species is permanganate, one that we produce and use as an oxidant, ironically, to treat for manganese sometimes. So it's a bit of a strange one. And that's manganese in the +7 state. So it takes 5 electrons per mole to transfer from 7 to 2 for permanganate to Mn2, for example. Iron Fe2 is soluble, some Fe3 complexes, and then there's also a strong oxidant we can make that is not yet commercially available. The solid forms are things like manganese carbonate precipitates at high pH with softening, and then various other minerals that we generally end up calling MnOX, because the X could be O2, in fully oxidized Mn4, mixtures of Mn3 and Mn4 or Mn3 itself. And iron usually precipitates as amorphous ferric hydroxide and then creates a lot of other oxides. So the removal part, simplifying it, is this. Dissolved iron and manganese needs to become a particle and get removed. That's one way. So we can turn it into particles, so oxidation and precipitation remove it, or that dissolved iron or manganese, usually manganese, gets to a surface, and I'll describe lots of surfaces, and we get it off that surface and take care of it that way. Another way to show it is from a publication I and my students did about manganese in 2016, but it can be extended to iron, is basically we say, is it dissolved or particulate from the start? And then we divide that into removing particles, or if it's dissolved, we make particles, then remove the particles, or we go on to sorption and surface oxidation, biological oxidation by a biofilm, or onto ion exchange occasionally, and meet our treated water goals. In all these cases, we either have a brine with waste, Mn and Fe, or we have a particulate, Mn and Fe. A process I don't list here and include is membrane filtration, RO or NF. Those can remove manganese or iron, but manganese or iron basically destroy, clog such processes. So they're never a primary objective at a commercial scale. Point of use is different. So here's an example of chemical oxidation and particle removal. We might have a groundwater, add an oxidant, and make particles, and then remove them with media or membrane filters. And they're surprisingly effective to me in some cases. The oxidants for iron can be anything: oxygen, free chlorine, strong oxidants. But for manganese, it must be a strong oxidant. Permanganate, ozone, or chlorine dioxide is needed to oxidize, and under most pH conditions, manganese to particles. On the surface water side, we have the similar thing. We're strong oxidants and weak oxidants. We give reaction time, but often there we're adding a coagulant and doing some pH control, and then coagulation, flocculation, and then particle removal, and do that. And the key there is to use coagulation to destabilize colloids of manganese, for example, or that get created, and remove them. So the two parts about chemical oxidation and removal that are basically how much and how fast. And those are fancy names for those are stoichiometry. So how much do I add of the oxidant to oxidize the manganese and the iron? And it turns out we need twice as much oxidant per milligram of manganese than we do for iron, because manganese is going from Mn2 to Mn4, and iron's going from Fe2 to Fe3. And by chance, they both happen to have similar atomic weights, 55 and 56 about. You've also, when you add an oxidant, have to satisfy competing oxidant demand from natural organic matter, other reduced species such as sulfide or ammonia, and we have to add in excess of that. We need to determine that experimentally, and can be done in jar testing. And then when you create particles from, say, iron or manganese, it can result in some unexpected results with stoichiometry that you have to study. And then how fast is reaction kinetics. So the rate of the oxidants reacting with these reduced metals is affected by pH, temperature, and some other things. And one of the things that happens is when iron co-occurs with manganese, the oxidant reacts so much faster with iron than with manganese. That first happens, and then manganese gets reacted if it's going to react. And iron is typically oxidized faster than the oxidation of natural organic matter to make disinfection byproducts, so that we can sometimes use free chlorine to oxidize iron only in the presence of manganese and NOM, and then proceed with other processes. And we can do nice bench scale things. One thing about chemistry and water treatment, it doesn't matter whether it's a beaker, a vial, or a treatment plant, the chemistry is the same. So to take particles out, I'm not going to read through these, but all the things we use to take particles: clarification, media filtration, or MFUF, particle removal membranes, each have their niche in the removal world. So you might find a groundwater that precipitates manganese with permanganate, makes the particles, and then strains them with a microfilter or ultrafilter. That has been done. All right, what about dissolved removal by media surfaces? So what I mean here is that we're going through we've got dissolved iron and manganese. We may or may not add an oxidant. We might affect the pH with some chemicals. We go through some tank or bed of granular media, either by gravity or by pressure. The metals get taken up on the surface, either a metal oxide, a biofilm, or ion exchange, and sometimes combined with particle deposition, and then we end up with good water. So one of the things about manganese is this: if we have any surface in contact with water, and it has in it reduced manganese, Mn2+, and free chlorine, HOCl, it will at some point create a manganese oxide coating on the surface. It gets started. It may be hard to get started, but once it starts, it's autocatalytic, because I'll explain that manganese oxide surface loves to take up some more manganese, and then it gets oxidized, and so forth. So we design it to happen in granular media. Unfortunately, it happens wherever this condition applies, such as water main and sample line walls of clear wells, and things like continuous chlorine analyzers. So be wary of sample lines that remove manganese and give you a false sense of the treatment plant removing manganese, because sample lines can be to the lab sink can be really good removers of manganese. Go to the source if you have questions about that. So the way this works is that an oxide coating, manganese oxide surface, adsorbs or complexes reduced manganese, and it can do the same with reduced iron. And then when that happens, the amazing thing is that an oxidant such as free chlorine will very quickly oxidize manganese when it's adsorbed, whereas in solution at pH 7, 7.5, 8, 6, normal water treatment pHs, free chlorine does not oxidize manganese to particles in the time frame of a water treatment plant. It does in the time frame of a distribution system, days or weeks, multiple days, but not in 30 minutes or an hour. It just doesn't happen. And that's a myth that's perpetuated in textbooks all over the place, that free chlorine oxidizes reduced manganese to particles just like ozone, chlorine dioxide, or permanganate. And it's just false. It's not true. Free chlorine can oxidize manganese to particles in rare circumstances. One of the cases happens to be, for example, Providence, Rhode Island. The pH is 9.5 to 10 when free chlorine is added. And yes, manganese is oxidized to particles on that case ahead of filtration for that rare circumstance. So then what about oxidizing? So the metals are taken up and they get oxidized on the surface. So it can be done continuously or intermittently. And continuous is when the oxidant's always in the media influent. And the most common case of this is free chlorine. Some folks think it happens with permanganate, and I'll explain some challenges with that. And actually, Bill Naki showed recently that chloramines can also cause this. Unfortunately, oxygen is not a strong enough oxidant to oxidize adsorbed manganese or iron. Well, iron it will, but not manganese. I wish it was. If it was, it would be a lot easier to deal with manganese. Mostly iron removal, if we add an oxidant continuously, is by particle removal, because the iron is so rapidly oxidized by any oxidant we add, just about under most conditions. The other method is what's called intermittent regeneration, where we run the metal oxide as an adsorber. It reaches a point where it's saturated, starts to break through. We stop the process, backwash the filter with permanganate usually, and oxidize the surface and backwash off particles and start again. So that's an intermittent regeneration. So there's kind of three classes of this. There's kind of three classes of the way this process works. One is what a lot of people refer to as green sand filtration. I don't happen to like the word, and I'll explain why in a minute. But it usually refers to groundwater, smaller media, pressure filters, and removal of iron and manganese, either intermittent or continuous regeneration. And it often actually is a combination of iron particle removal and Mn removal by sorption and surface oxidation. A lot of people don't understand that that's what's going on, but it is the case. The second one is that normal media used in surface water treatment, for example, to remove particles, that media can get coated with manganese oxide and can also effectively adsorb manganese. And if there's free chlorine across that filter surface, the manganese will be oxidized on the surface and removed that way. So that happens quite a lot. The third, and I'm going to spend a little more time on this with some examples, is a manganese contactor after we do particle removal. So move the step for uptake beyond the particle removal step. And I'll say more about that. So some of the media that's used, this is a picture, and they look about the same, but the one in the lower right is actually original green sand. It's glauconite. It's a mineral. It actually is green in the right light. It's mined, and it was used. It's a natural ion exchange media. And somewhere along the line, before the 60s, in the 40s, 50s, 30s, I'm not sure, someone must have hit it with chlorine after it had adsorbed a bunch of manganese, and it turned black. And it turned out it was better to remove the manganese after it turned black. And so that got called manganese green sand. And then over time, people dropped the word manganese, so called the manganese coated green sand. But green sand is the original media. Since then, we don't really mine it anymore, but companies like Inversand make a product called Green Sand Plus. That's a manufactured media with a manganese oxide surface. But it turns out any media can get a manganese oxide surface. These are some pictures of plastic media, for example, an upflow roughing filter, that on the right side is the manganese coated, and on the left is the manganese extracted in the lab. Silica sand, one side extracted, one side coated. And ceramic media, that was in this case purchased as the uncoated and then coated in the field to make the coated media. And then pyrolusite is manganese oxide, and there's only one picture because if you dissolve that, there's nothing left. So a typical green sand approach involves things like a pre-oxidant addition, which we may add. The groundwater, either permanganate or free chlorine or both. If you have iron and or you add permanganate with manganese, you're going to have particle filtration, not sorption and surface oxidation, because you will already made particles ahead of the media filter. And if we add free chlorine, on the other hand, it will be sorption and surface oxidation. If present, iron is usually oxidized to particles and then so much faster than manganese, and we remove it as particles. Some of those particles sorb some of the Mn2 plus, and we'll remove that. And I have a note on the lower right about manganese oxide coated media and permanganate. You can't have permanganate leaving a filter, unlike free chlorine. It makes the water pink, and it precipitates later on as manganese dioxide. So, in my opinion, plants that add permanganate in front of a media filter like this and don't have problems, the permanganate is all reduced before it gets to the media filter and creates particles that luckily fortunately get removed. Regeneration, again, is either continuous. It works great with free chlorine and manganese. Continuous is permanganate's challenging, and I just went through those points, so I'm not going to say them again. And continuous with permanganate and free chlorine can work well. You put a low dose of permanganate and then add free chlorine after that. And intermittent regeneration provides absorption, but it will break through ultimately. Now, particle removal in filters. This is the case where we have normal anthracite or sand in a particle filter, and it gets coated with manganese oxide, and it will take up manganese as long as there's free chlorine continuously across it. And it's really a great process. Okay, it really works well, and it regenerates the media. Things backwash, and people have been doing this for decades and decades, for a long time, not knowing it. And then in the last 30 years, myself and Bill Nocky have done multiple projects explaining this. An example of data from one of those. So I see there's some questions in chat. I really was going to wait till the end. That's up to you, Abby, to say, because I think I'm got a chance of losing too much time. So
if you want to answer that one, you can.
Okay, so there's a question about permanganate. I have to pull up the chat, which I have to find. Chat. Where is it? Somewhere. Chat. There.
You want the last one?
I have a last. You say William Denko says potassium permanganate in filters may not deposit. Can you go over this again? So potassium permanganate is a salt that dissolves in water. So it's permanganate. That's a dissolved ion. It's pink. It makes pink water. It reacts with reduced substances like iron or manganese or other things, and it becomes reduced usually to manganese oxide itself. So it makes particles. And those particles that are created from permanganate, not from the original manganese, need to be removed. And they sometimes are electrically stable. They're best if that's done before coagulant addition. But other times, if there's precipitating iron, they can be effectively removed as a particle removal. So that's what I mean by that. All right. So permanganate, you can't have it existing in water you deliver to consumers. It makes pink water, and then it precipitates as manganese oxide. All right. I'm going to continue on from there. So an example here is of coating levels on media from a filter. So the x-axis is manganese coating, milligrams of manganese per gram of media. And this is a standard dual media filter at a plant that received pre-filter chlorine and seasonally has reduced manganese in their source water. And they have 20 to 40 milligrams of manganese per gram of media. So it's a big coating. And it's all in the top because it gets removed and doesn't really get to the sand in the bottom. It's a dual media filter. So that's the way that one works. We did lots of pictures of that. For some reason, my slide doesn't want to advance. Let's see if we can. There we go. And the way that removal works is, again, the oxide coating is here. Mn gets absorbed, free chlorine comes along, oxidizes it, and it just keeps growing as a surface. One of the problems with that, though, is that there can also be natural organic matter. And natural organic matter may be on the surface. Here it's just shown as a squiggly brown line. We may have iron or aluminum flock that's got NOM with it, because that's why we're doing coagulation, and that's there. And the free chlorine that comes along can oxidize that natural organic matter and make disinfection byproducts. And we know that continuous free chlorine across a media filter like this does most of the time make more DBPs than it would if it was added after the filtration. And I have one cited here. So the third option is, let's make the dissolved manganese removal a separate process than the particle removal. Let's do it in a manganese contactor. It's another stage of a media process that we add after. So I've got it shown here in this schematic after particle removal. And this has been done a long time in the United Kingdom, two-stage filtration, but the contactor stage is not designed for just dissolved uptake. And we've been working on this for dissolved uptake. And here's the difference for the contactor. The contactor is typically ceramic or anthracite now, what we've gone to, lower density, lower weight, versus a standard media filter, anthracite, coal, sand, carbon. We don't use carbon in the contactors because carbon kills chlorine. So we can't have chlorine and carbon together, don't work so well. Effective size of the particle filter is 0.4 to 1 millimeter, whereas we can go 2 to 10 millimeters. We can go very high. Practice, they've been 1 to 2 millimeters. Loading rates for filtration are typically 2 to 6 gallons per square foot, but we've operated contactors 10, 20, 30 gallons per square foot, and it works great. And free chlorine is present across a contactor where it's not for a media filter that doesn't have. If we don't have free chlorine, then it's a bioactive filter, or can be, and it's a good process. So initially, lab work was done by Professor Bill Nockey down at Virginia Tech. He was doing that at the time we were doing some studies for Aquarian. We shipped the column up. We started doing lab research and pilot testing for Aquarian Water Company in 2013. They put online a full-scale plant they designed on this process, and I actually spent the entire day yesterday at this water treatment plant doing lab work. And new plants, more recently in 2022, include a groundwater source in Brunswick, Maine, surface water source from Groton, Connecticut, and others, and I'm leaving some out. So the case study of Lantern Hill is illustrative of the process. We've got a groundwater well source. It's got dissolved iron, dissolved manganese, and natural organic matter. Not a fun mixture. So historically in our business, people would talk about groundwaters and not worry about NOM. It's become less and less true, and levels of NOM in groundwaters in New England have been rising over time in our experience. So in this case, this plant increases the pH with some base, adds free chlorine or permanganate and some cationic polymer. It goes through dew media anthracite sand filters to remove particles, which include natural organic matter and iron. Then free chlorine is dosed now, and it goes across a manganese oxide coated macrolite. That's a ceramic media contactors, and for manganese removal. So the way they look, I was standing next to this contactor all day yesterday. It's just a pressure vessel. Inside the vessel is the macrolite media. They were designed at 10 GPM per square foot. They backwash, in this case, they're backwashing now about every 20 days. We first started out 4 to 6 weeks. And the accumulated manganese oxide that precipitated on the surface, not as particles, is removed. And it takes about 30 seconds to go across that media. So the way iron removal works across the plant is it comes in at, say, 2.5 milligrams per liter. We add a base and pH control, make it all particles. That's the black thing here, all particles. Dew media filter removes it all. End of the iron story. We're all good with that. So free chlorine is added between the dew media effluent and the contactor. So the story with manganese is very different. The manganese comes in around 0.25, 0.23. That's what it was yesterday. Free chlorine in this case was dosed to oxidize iron, and it oxidized the iron with no residual. The manganese is not removed by the dew media filter to any extent. A little bit came out with the iron. Then free chlorine is added. This is what's going into the contactor, all dissolved manganese still, and then it does a great job removing it down to less than 0.02 milligrams per liter. And the reason this was done in this way was to prevent this small groundwater plant from being a disinfection byproduct factory. Previously, back in 10, 11, 12, it could go as high as 150 to 200 micrograms per liter of either HA5 or THMs leaving the plant. And the plant is shut off, used seasonally, so it would be shut off. And they were even risking stage 1 DBP compliance. So the plant went online in 2013 and put out this kind of levels of DBPs. They have crept up a little bit because natural organic matter has crept up. And we continue to work to optimize that plant. Another case is in Brunswick, Maine, where a groundwater has intermittently regenerated MN oxide coated green sand type filters that are intermittently regenerated with permanganate. The residuals go to lagoons. Then this plant uses fixed bed anion exchange to remove natural organic matter to control DBPs. Then free chlorine is dosed. It goes across some manganese oxide coated anthracite media contactors and into the distribution system. And it looks like this. That's a bunch of pressure vessels. And it has this beautiful walkway near the top. These are the media filters. These are anion exchange. These are the manganese contactors. And from an operator perspective, it's wonderful. This is a CDM design. The hatch is right there. You can open it, go in, and get to the plant. It's nice. And Tonka became Kurita. And I was really thrilled when I saw they had a nameplate label called Manganese Contactor. This took a long time to convince people it's not a filter for particles and to call it that way. So I was excited when that happened. So that's my romp through manganese. I think we've got a poll question, and then Abby's going to say, and I'm going to say a few more things about the program. So if you could launch that poll. All right. Looks like Danielle's launched it. So EPA health advisory level for manganese. And I guess it's in 2 questions, right, Danielle? You got it. We're getting there close to.
Yes, it's a two-parter.
Yeah. Okay.
Try to get to 80%.
Yeah. All right. Well, we're good, I think, Danielle, right?
Yep. All right.
Okay. So the answer is 0.3. You don't read off the answers, the distribution. Let's not use that time. But the answer is 0.3. That's the health advisory. Let's go on to the next question.
Yeah. What is the recommended goal for the level of manganese after treatment?
Yes. Sorry, I was supposed to read that.
That's right. Sometimes presenters can't see the poll when it pops up, so I just want to make sure.
I am seeing it. I'm seeing it. So I'm seeing that you're doing it, I should say. Again, when we get in there. Doing good. Looks like folks are doing good. All right, so we're kind of at the place where we're going to be. All right, Danielle? Yeah, so the answer there is the goal recommended is 0.02. The EPA secondary maximum contaminant level is 0.05, but that's often causes chronic problems. It's not good enough in many of us' opinion. All right, thanks for the poll. Looks like most everybody has on top of that. So a couple of quick things on our program with UMass has been partnering with MassDEP for over 10 years on a variety of helping them implement programs. And this particular case, we help hire some technical assistance providers who work part-time to help small systems, all the small systems with the various aspects of getting a grant, getting it implemented, getting off the ground, and getting going. So we have assistance providers that are working in that area. That's one of the things we do. And another is that we can engage in some lab and small scale pilot work. We have a mobile water innovation laboratory, and we haven't actually implemented one of these yet, but are contemplating a couple different options. We can do bench scale lab services, and we have some resources within the grant to pay for some of this to help some small systems. And so there's a document here with a link to it that describes these services in more detail, but we'd be happy to communicate about that. So those are a couple of things that are on the UMass side of this. And there are two grants actually, and we recently also were able to, through one of the grants from US EPA to DEP, buy some equipment that we can do some of PFAS measurements, for example, to support others in doing their programs. And now I'm going to hand it over to Abby. Oh, after here's some of TA provider contacts: Eric, Christina, and Adam. And you'll hear a little bit more about Adam in a minute. And then I think there we go. I'm going to pass it. I'm going to make myself disappear, and Abby, take it away. And I'll tell me what to advance. So.
Yeah, no problem. Thank you, John. Appreciate it. So I'm Abby Jacobs, the Emerging Contaminants in Smaller Disadvantaged Communities Grants Manager at MassDEP. So I'll go through these quickly because we're running out of a little time. Want to allow for Q&A. But this provides grant funding to public water systems or communities to plan, design, and construct long-term solutions to address emerging contaminants. And that includes PFAS and manganese and all of those that are on that CCL list as well. So lots of different activities that could be related to addressing emerging contaminants could be through research and testing, non-routine testing, pilot testing, that sort of thing. Planning and design, whether or not your system is looking at maybe treatment or maybe an interconnection with another system. Source water, maybe you need to dig a new well or do some test wells or things like that. And consolidation of systems and lots of other ones. So you can go to that link for other examples of activities addressing emerging contaminants. So eligible entities are community public water systems, and this can be publicly or privately owned, or nonprofit, transient, non-community systems, or non-transient, non-community water systems. So these systems need to be located in a community in the Clean Water Trust Disadvantaged Community Program, or serves a population less than 10,000. And if you're just a small system, then there's some extra hoops you got to jump through. So that PWS that's only small and not disadvantaged would have to show that they lack capacity to incur debt sufficient to finance the project. So if you have questions on that, let me know. There is a few for-profit systems and TNCs that would be eligible if they were doing an interconnection as well. It's like special eligibility. So reach out with that. And the key here is if you're interested, please complete a needs assessment survey form, and that's found on the MassDEP ECSCC website. And that just shows us that you're interested in the program, and we'll review that and get right and that is the program.director-gwp@mass.gov. So I also want to note that this grant is not competitive and it's still open with rolling admissions. So kind of as we get needs surveys and make decisions on a rolling basis. All right, so the next slide, please. The other grant I want to talk about is a new one that we have. It is called the Engineering and Design Plans Grant Program. And this is set up a little differently, but is related. So it's engineering and design plans provided to public water systems by a pre-approved engineering firm that we've already approved to address long-term solutions for emerging contaminants in drinking water supplies. So similar kind of project plans that can be done to ECSCC. So you'll see those listed there. I won't go into that here since we're running out of time. Eligibility for this one is slightly different than the ECSCC grant, but it is community public water systems that are publicly or privately owned, or a nonprofit, transient, non-community, or non-transient, non-community. And the key here is that you need to be a small system and located in a disadvantaged community and have an emerging contaminant issue. So for-profits are also eligible for community systems, but are a little lower in priority. So it's a smaller grant supported up to $500,000 in funds and provides up to $75,000 in engineering and design costs per project. And that's paid directly to the engineering firm. So apply here. You click on that link there when you download these later. And this one is one we launched recently, about a month ago. So the grant is still open with rolling admissions. And same as ECSCC, better get in on it earlier rather than later as well. So next slide. Okay, that's just any questions for MassDEP. Our contact information is right there. And I think there's one more slide. All right, so certificate requirements, make sure that you complete the evaluation at the end of the session, which launches after you exit, and a link is also included in the follow-up email. And you'll get your certificate within 2 weeks. So how about we stop the recording there and we can